Next, we'll look at the fundamental theorem of calculus. So it says that if f is a continuous function on a to b, so that's on the interval from a to b, and f is any antiderivative, then you can compute that area that we want, the area under f from a to b, by just taking that antiderivative and plugging in the larger bound or the upper bound, and then subtracting off the antiderivative evaluated at the lower bound. So this is the connection between the area interpretation of the integral, and the antiderivative that we've been considering. So this is sort of the nice, quick way of computing these areas, just like we had some nice, quick ways of computing derivatives using things like the power rule or the product rule or whatever. The fundamental theorem of calculus is essentially how we're going to compute any definite integral. So this just says that if you want the area between a and b, you should just first compute any antiderivative that you'd like for that function that you're integrating, and then you can plug in b and then subtract the evaluation at a. So let's use that to evaluate this particular integral. So we want the integral from -2 to 2 of t squared minus 4. Now the way that we're going to do this is we're first going to evaluate the antiderivative. So we'll find the antiderivative for t squared minus 4. We know from last week's material that to integrate t squared, we should add 1 to that power and then divide by the new power. The same thing is true for the -4. So if we did that, we would get a -4t. We know that the antiderivative of -4 is -4t. So this is an antiderivative. You can actually use any one that you'd like. So you could have a plus c here if you'd like. But you can choose any antiderivative that you want. So you could choose the +0 version, you could choose the +7 version. Any of those are antiderivatives, and they'll all give you the same answer at the end, and I'll explain that in a second. But I'm just going to stick with this simple antiderivative. So I'm going to choose c equals 0 here. And that's normally what you'll do whenever you choose an antiderivative. You normally just ignore c whenever you're computing a definite integral, because c will go away at the end anyway. Okay, so this is the antiderivative, but remember, to finish this problem, we need to plug in b and then subtract what we get whenever we plug in a. So I'm going to introduce some notation for that. Whenever we need to plug in a couple of values into this expression, I'm going to write this little evaluation bar. So I would read this as this function evaluated from -2 to 2. And the interpretation of this is that we're going to plug in 2 into this parenthetical expression, and then we'll subtract what we get whenever we plug in this lower value. So in other words, this is just a shorthand for saying that we plug in 2 as our t value. That would give us this. And then we subtract what we get whenever we plug in the lower bound here, which is -2. So if I plug in a -2, that would be a -2 cubed over 3 minus a 4 times a -2. And this is the value of this antiderivative. So let's clean this one up a little bit. Again, I'm not really super concerned with you cleaning up your answers, although in cases like this, it might be good in case there's any cancellation. Whoops. So a 2 cubed would be an 8, so that's an 8/3 minus 8 for the first parenthetical term. And then for the second parenthetical term, I would get a -2 cubed, which is a -8 over 3, and then a +8. Now, the main thing that I want you to be careful about here is that the minus sign that appears in the fundamental theorem of calculus, that applies to the entire right expression here, f evaluated at a. So in other words, this minus sign is going to apply to everything to the right of it. So that means we need to be distributing this minus sign. It will apply to both of those terms inside the parentheses. So this minus sign distributes. And that would leave us with an 8/3 minus 8 for the first couple terms. And then if we distribute the minus sign to this first term, we would get a positive 8/3. And if we distribute the minus sign to this second term, we would get a negative 8 again. And that would leave us with 8/3 plus 8/3 would be 16/3. And negative 8 minus 8 would be a negative 16. And I'm not going to worry about combining these over the same denominator. I'll just leave it like that. So that's the area under this particular curve between -2 and 2. And in this case, it happens to be a negative area. All that means is that this area is below the x-axis. So if you were to graph this function, it looks something like this. And we're integrating from -2 to 2. And what we just found is that this value over here, if you were to plug that into a calculator to get like a decimal value, the decimal value that you would find is the area of this region underneath the x-axis, but it'll be negative because remember that any area beneath the x-axis is counted as a negative by this integral. So that's the reason that this ends up being negative. So the last thing that I want to do in this video is just justify to you why you can choose any antiderivative that you want. So why is it the case that this formula gives you the same answer no matter what value of c you choose before plugging in? So I want to show you that c actually doesn't matter when you're doing definite integrals like this. We still need c anytime we do a general antiderivative, which is also called an indefinite integral. So if you don't have these integral bounds, if a and b are not there, we'll still need to write plus c as part of our answer. But if a and b are there, it turns out that you don't need c. And here's why. So here's the problem that we were just working on. Let's say that whenever I integrate, I find the antiderivative of t squared minus 4. Here's its antiderivative. It's t cubed over 3 minus 4t plus c. Now, and again, I'm using this evaluation bar notation. This means that I've taken the integral, but I now need to evaluate from -2 to 2. So that means that I'm first going to plug in the upper value, and then I'm going to subtract what I get whenever I plug in this lower value. So here's what I get if I take the thing in parentheses up here and I plug in a +2. So that would be a +2 cubed divided by 3 minus a 4 times that +2 plus a c. So anytime you have a constant, whenever you plug in something like 2, it's just going to stay that constant. So this will still just be a plus c for that first evaluation. And then the fundamental theorem of calculus says we need to subtract what we get whenever we plug in the lower bound. So this side is what I get whenever I plug in that lower bound, which is a -2. I would get a -2 cubed over 3 minus a 4 times a -2 plus a c. And now let's simplify this. So if I simplify, then I would again, for the first term, get an 8 over 3 minus an 8 plus a c. And then for the second term, I would get a -8/3 plus 8 plus c. But remember, I still need to distribute that minus sign to this entire second evaluation. So I would distribute the minus sign. When I do distribute the minus sign, I would get an 8/3 plus another 8/3. So that would give me this 16/3. And then I would get a -8 and then another -8 from this minus sign. So that would end up giving me a -16 like we had a second ago. But notice what happens to these c's. So here I have a plus c. But over here, I would also have a plus c that gets a minus sign whenever I distribute. So I end up getting a plus c minus c. And this will happen with any antiderivative that you choose. So for any function where you take an antiderivative, if you included the plus c and then you do this evaluation, one of them will have a plus c and one of them will have a minus c. And therefore, those things will cancel out. Plus c minus c ends up being 0, and therefore at the end, you'll get the same answer that we got earlier, which is 16/3 minus 16, no matter what value of c we chose. So for that reason, we're normally going to ignore c whenever we do definite integrals. So if you have integral bounds, you can ignore c, and you'll always get the same answer at the end.